Welcome to today's ATENA webinar. It's very nice that you could join us. My name is Michaela Herzfeld, and I'm part of Červenka consulting team. And today we have the topic durability analysis in ATENA 2025. So I will jump into it. So when it comes to durability analysis, there are actually like three aspects that we are considering in ATENA software, which is like environmental conditions where the reinforced concrete structures are placed. And maybe I should emphasize a little bit that we will talk mainly about reinforced concrete structures because it's related to corrosion of reinforcement very much. And also, beside environment, it's important the composition of the material of the concrete. And last part is also like the design of the structure, which is like mainly concrete cover. Here you can see some examples of the calculations in ATENA. And yeah, we will focus on that. So in ATENA, there are basically two types of durability analysis. The first one is the carbonation and chloride effect on the reinforced concrete structures, because it mainly focused on the corrosion of the steel. It's like, of course, like carbonation and chlorides, they're penetrating the concrete, but once they reach the reinforcement, they can trigger the corrosion. And the other part is alkali-silica reaction. Maybe I will just switch my pointer, that it's visible a little bit better. Alkali-silica reaction, which is important just for concrete itself. And it basically considers the reaction of aggregate that has to be reactive, the specific silica aggregate, and which is in combination with alkali producing some secondary alkali-silica gel in the structure of concrete, and that can, on the macroscopic level, cause the expansion of concrete, which is connected to developed microcracking inside the structure. And it causes like reduction of mechanical properties of concrete. So first of all, there is model for carbonation and chlorides, which is very much interconnected. And it's basically 1D model of penetration of either carbonation or chlorides or both through the loaded surface. So in ATENA, you basically say that some surface of the structure is loaded with these conditions. And through the surface, there is like 1D model that is searching for the embedded steel in like shorted direction from the surface. And depending on the pollution, which is like during the initiation period, we are checking the pollution, like if the carbonation already reached the steel or chlorides have the high concentration on the level where is the placed the steel inside, and it can start to trigger the corrosion of embedded steel. And this period, when the pollution is like collected inside the structure through the concrete cover, it's called induction time. So induction time tells you the moment when the corrosion of steel will be triggered. And from the initiation time, we go to propagation time, when the pollution is like high enough to trigger the corrosion. And it can also lead to cracking and spalling of the concrete cover. So then I will like divide now the model between the carbonation and then chlorides, because we have like different formulas for it. For carbonation, we also divided for carbonation of uncracked concrete, where you can see this formula that is for carbonation depth, where it reaches like from the surface. How is the carbonation depth distance from the surface that is loaded? And this carbonation depth, of course, depends on the concrete composition, how like that involves the diffusivity, which is like this rather like bigger formula that mainly consists of like composition of concrete and also the relative humidity of the environment. And also important information is, of course, concrete cover. So when I jump into this ATENA 2025 preprocessor interface, you can see this is like interface for carbonation boundary condition. There are input parameters. So this is like part that is related to material composition, water, cement, and cement supplements. And this is parameter that is related to which type of cement supplement it is. Then there is environmental conditions, which is concentration of carbon dioxide in atmosphere. Default is there like 360 ppm, but nowadays it might be a little bit more, like 400, 420, something like that. Then there is like this relative humidity of the environment, and also you need to specify the concrete cover. The rest is for corrosion. We'll get to that a little bit later. So I was talking first of the carbonation of uncracked concrete, but once the structure develops some cracks, it will accelerate the penetration of carbonation. So the carbonation depth is accelerated by the crack width directly in the formula. And like here in the table is example for the same concrete structure. There is this induction time, which is the time when the corrosion can be triggered in the structure. So when the crack width is 0, so there are no cracks, it can be like 246 years, this induction time, before any corrosion starts. But as you develop crack width and you get to like 0.3 millimeters, it can drop to 39 years. So it can have really big impact on the service life. So then we go to chlorides. There is like general formula for cracked and uncracked concrete. It has like a little bit different approach, because diffusivity for carbonation here, I mean for chlorides, is developing in time, and for carbonation there was like constant one. So this diffusivity for chlorides is decreasing in time, actually. And it basically is based on some reference diffusivity in reference time, which is something that you can have from some measurements. And there is parameter M that is related to what sort of exposure you have for chlorides, if it is like structure that is submerged in seawater, or if it is just sprinkled with it, something like that. And it's for some time of interest, which might be like, I think in ATENA we have 30 years in general, but after that the diffusion becomes constant, or diffusivity for chloride. So again, this is like interface for chlorides in ATENA 2025 for the boundary conditions. So you can see what are the parameters that I just mentioned, and yeah, we will get to that also during the example. So when we have like either carbonation or chloride that are penetrating the concrete, they can reach the reinforcement and trigger corrosion, which is like then we are getting to propagation phase. And this corrosion in ATENA is basically like corrosion rate in radial direction. It's shown here. This is like cross section of reinforcement that is corroded. So the orange line should show like some sort of initial cross section, and the inner part shows the cross section of reinforcement that is still non-corroded. And here is the radial direction, how the corrosion is propagating. And this corrosion rate depends on corrosion current density, how it is developing in time. And it's different for carbonation and chlorides. So for carbonation, that corrosion current density ranges between 0.1 to 10 microamperes per square centimeter. And it basically depends on the relative humidity of concrete that you enter as an input parameter. Then there is like corrosion current density for chloride that has a little bit more complex formula, and it assumes the chloride content and the temperature as well. This is a corrosion parameter that basically says if it is like uniform corrosion or some pitting corrosion or more localized corrosion. And it depends also like on time that it's developing in time. What is maybe a little bit interesting here is reinforcement corrosion parameter that you can actually find easily in post-processing that will tell you like how the corrosion is proceeding on the reinforcement, and it's ranging between 0 and 1, and you can see the formula here that it's 1 minus, and it's like a division or ratio between the remaining area that is not corroded to initial area. So once it is 1, it's completely corroded. If the reinforcement corrosion is 0, that means that there is no corrosion happening on that reinforcement. Okay, so we were talking about the corrosion rate, and this corrosion rate in propagation phase can also cause cracking or even spalling. So for cracking and spalling, we use the Duracrite model that gives very realistic results. So critical penetration depth for cracking is based on this formula where it's like concrete cover, initial diameter, and this is characteristic split tensile strength for concrete, and these parameters are actually given from the Duracrite model. It can also proceed to the spalling, where the critical penetration depth reaches like this value that it causes spalling. It depends on critical spalling width of the crack, which is defined in ATENA, and also initial crack, which is like taken from the simulation. And that there is parameter B that depends on the position of the bar where it is placed. So if it happens that it's cracking and even spalling, then ATENA assumes that the bar is basically exposed to the atmosphere. And in that case, there should be defined also some corrosion rate once the bar is completely exposed. So this is something that you can find also in our documentation, what sort of corrosion rates are like recommended for certain conditions. And that is actually like, this is part of that boundary conditions that is defined in preprocessing for both, like either carbonation or chlorides. This is regarding the corrosion, because that is the same for both. And here you can see that corrosion rate, it might be changed like corrosion rate in atmosphere, like in atmospheric conditions. So this is something that you add, but that is basically in the moment when falling is assumed. Then you have the splitting tensile strength of concrete and corrosion parameter that is, as I mentioned, assuming if the corrosion is uniform or pitting corrosion. This parameter is actually the maximum reinforcement. That is important that you add some reasonable value here, because default is 0, but this is actually parameter where you say how deep from the loaded surface you should search for the reinforcement that might be affected by these conditions. And if there is 0, then it's not searching for any reinforcement. So it should always be something a little bit higher, that you reach at least the first reinforcement or even deeper in the structure. So now, I mean, it was a lot of theory, a lot of parameters, and I would like to jump into preprocessing, and later when it's calculated, also the post-processing of such analysis of chlorides and carbonation. So I will show you in preprocessing how to define the boundary conditions. Important part is also a time mapping, because we are working with static analysis, but we can map the time even in static analysis. Then I want to show you how to work with loading history, which is also shown here on this diagram. This is like LD diagram for the structure, and it basically shows like that analysis can be divided in like multiple steps. We call them intervals. So this one is like example is for intervals. As you can see here, the first one is loading just with the self weight. Then there might be some general loading, the next interval, where you assume some sort of combination that you expect, like combination of loading that you can expect on your structure. Then the third part can be corrosion, when it's like the structure is loaded and then it's exposed to some environmental effects. And after this period is finished, then you can also test with overloading the structure, how it affects the load bearing capacity to be exposed to some corrosion. And then you can also do the same analysis without this corrosion part, for example, and compare the load bearing capacity for the structure that was not exposed to any environment or some harm of these effects. Yeah, and because like even these analyses specifically have a lot of different parameters that are ranging, and some of them you need to like either find in the literature, or you need to base it on some experiments. It's good to check 2 of our manuals for this. It's like either ATENA input manual or theory manual. I will maybe just jump into it quickly. When you go to our ATENA Center there is easy to find the documentation, and they're like ATENA input file format, because that is actually very helpful when you are checking from time to time also your input file, that you can find all the parameters in here that are more like described or giving you more explanation than you can sometimes find in the theory manual. But of course, it's good to also check the theory manual. Sometimes they complement each other in certain parts, so it's good to work with both of them. Well, now I would also like to show you here that there are tutorials. We have this aging management part, which has two examples, carbonation and chloride attack. As you can see, it's the same structure. So I basically borrowed this structure, so you can also test it on your own with this structure. So I borrowed this structure, and we will go through just those extra steps for the durability analysis. So I have this beam that is part of our tutorials, so it's always part of the installation, and it's basically a model on its own. Everything is defined, like materials and meshing and all the boundary conditions that it's supported and so on. And we will just do now those like specific steps for durability analysis. Where we need to start is, like, we will focus basically in this last section, analysis. So we need to start with defining the load case, because there are some load cases, but there is not the load case that is specific for corrosion that you can see in here. And one thing that I would like to point out here is that you have application method in here mentioned. In this case, it's total. And otherwise, if I save it, it's visible in here. Otherwise, it's working as incremental. So this is a little bit specific boundary conditions that are like for this sort of for this load case. There are other total conditions like fire, or it's probably mostly in the transport analysis. So you need to focus on when you are like working with loading, that you are loading it always like 100% in the loading steps. I showed you in the file later on, but at least I wanted to point out that here you can see where you need to focus on, where should be placed the complete load in every step, or where are just the incremental parts that it can be divided into smaller steps. So we jump into the boundary conditions. Again, it's mostly already defined for the structure, and now we are going to apply boundary conditions for carbonation and chlorides. As I mentioned, these boundary conditions for the chloride and carbonation are defined for the surface. So we go to create new condition on the surface. Then we have to choose the correct load case, which is corrosion. And I will first start with carbonation. So these are the parameters that we need to specify when it comes to like water cement mass. It's actually like this is in default unit, so maybe we can switch it to something that is more common for engineers. And for water and cement mass, it's actually cement mass 400 kilograms per square meter. It's quite good concrete, so we can maybe lower it to the half and make it some more ordinary concrete. Another parameter here, this is like the cement supplement mass, that is like silica fume or fly ash. We can consider that there are no added supplements like this. So we can also skip this parameter because that is specific for which type of the supplement it is. You can find it in our manual, what sort of values should be entered depending on which one it is. Then we have here the concentration of carbon dioxide in atmosphere. I would increase it a little bit because I think that nowadays it's standard 400 ppm. This is like relative humidity. Maybe I should mention just a small thing that relative humidity that is below 0.5 or like 50%, it basically stops carbonation. So it needs to be higher than 50% that there is trigger the effect of carbonation. Then we have like concrete cover. It depends, of course, on your structure. We can put like 4 centimeters here. And this is the here time mapping function. That is important part for this topic analysis, how to translate it into time during the analysis. So what I would try to do in general in here, it's to keep the units that are same like the default units to avoid any problems. Maybe can I open it here? Okay, I will save it and then I go back. So when you go to settings and projects, you can see default units. So unit-based system is like this, and the time unit is day. So then we can go back and work on it. So we were in time mapping, so days. This is something that you already need to have it connected a little bit to the loading history that you are going to do. I already know how it will look like the loading history, so I will enter it. And when we connect it with the loading history in task settings, I will go back also to show you one more time to see the connection between that. So basically what you do is like the X values are the steps in your analysis, and the Y values should be the time that is related to it. So I mentioned before that we first will load the structure with like self-weight and some load before we let the corrosion happen. So we will definitely not start the time directly at the moment when we are putting self-weight, because we will start the time at the moment when the corrosion starts, or no, not corrosion, but like corrosion load case. So that will be like when we assume the start of carbonation or chloride effect. That should be the step of the first like step of that interval. So in here we are like 0, 0, like first point is at the beginning of the loading history. And I already know that we are going to have like 30 steps before we start any corrosion. So at the first 30 steps, we have still 0 corrosion, because it will be, sorry, I'm saying corrosion, but corrosion can take some time. I mean corrosion load case. And we will let this corrosion load case happen for 20 steps. And these 20 steps should have the time frame, and we go from like 0 time to some certain time how long we want this durability analysis to go to that corrosion load case. So let's say that in our case we go for 100 years of exposure to carbonation and chlorides. 100 years, and we have to put it in days. So it's like 365 days times 100. So this is our time mapping function, because this part will be from like 0 steps to 30 steps in loading history, whereas some other preloading before we assume that the corrosion loading case starts, and when it starts we map it to the time. Okay, so from time mapping we continue with parameters here. This is maximum reinforcement depth. It's important parameter that it doesn't stay 0, otherwise ATENA will not search for any reinforcement that is embedded. So we always need to put there something reasonable, like, I don't know, for example, 20 centimeters deep, that it will search for any reinforcement that can be affected by the carbonation. Yeah, we will leave the same relative humidity because this one is for carbonation and this one is for corrosion. Splitting tensile strength, that of course depends on the concrete that you have. So I can leave this one as an example. And this is a corrosion parameter that depends if it is like pitting corrosion, uniform corrosion. That is something that you can find in the documentation what you prefer to apply. So we save it, and then I will change this wireframe model to solid, because then it's a little bit easier to assign the boundary condition, because now I have this carbonation boundary condition selected, and I use this unassign sign button to select the surfaces where I want to apply it. So we basically apply it everywhere from the bottom, that we can assume that will be exposed to atmosphere. As I'm clicking here and they're getting red, they're selected, and you can also see in here with this arrow how many entities you have selected already. Everywhere. Sign, and with enter I finish the signing. And yeah, so the carbonation at this moment is assigned. Yeah, it's good from time to time to save it, of course. And now we go to chloride to assign the new surface boundary condition, and we go for chloride. I would also divide it. That is just like for showing you that it's possible, not really any special reason, but we can divide it into like the vertical parts have a little bit different conditions, or not different conditions. I will have basically the same conditions. I will just assign different concrete cover in this case. And so I can rename it, that I know where to place this one. This one I need to just exchange it. I know the proper values. So reference diffusivity, it's something that you have from measurements. You should have also some reference time where it was like to which time frame it depends. Then there's this parameter that is like if it is like submerged or sprinkled or something, that is related also to the time frame. and after this time frame, the diffusion will be considered constant. Then you have like information on how much chlorides are in this on the surface penetrating the structure. So these are some values that we had from another case. So for this vertical condition, I will assume that it's a little bit thicker concrete cover. This one is, again, as I mentioned, in carbonation boundary condition. Important that ATENA is searching deep enough for the reinforcement. Here, splitting tensile strength, this is unfortunately incorrect. That's really small, but it should be something like 3.5 megapascal. And this one is actually pretty high. It should be smaller. Something like this. Corrosion parameter we can keep as it is. That is fitting corrosion, uniform corrosion, depends. And here automatically it will give you another time mapping function that you can use different one. But we already defined this 12 time mapping function for the carbonation, and we want to use it same way because we will apply both boundary conditions at the same time. But of course, you can have different time mapping functions in case of you are using this exposure time for like different time periods after different loading history. Yeah, cement mass we can leave, and also the temperature offset. I will save it, and it will automatically go to this selection that I can assign it. So I will put it just to the vertical pieces on a side like this, and then I can easily select this condition and copy it. Then go there, and what I want to just change, it might be like there might be different concrete covers around the structure. So you can save it, and again with button assign on assign, you can assign it to the rest of the parts where you want to apply this condition. So I will select all the other ones that are not like from the bottom, same like carbonation from the bottom, everything except those vertical ones where it's already assigned. So this is like boundary conditions. Here in the analysis, you can also notice that last part is functions, where you can find all the functions that were defined throughout your creation of the model. And here you can see also the time mapping function. Maybe I can also change it that it doesn't show time, because this is basically just steps. So simply it has no quantity. Okay, so we have prepared the load case. Thanks to that load case, we were able to create and assign boundary conditions, and in task we can create the loading history. So I will define loading history in 4 intervals. So I will create here 4 intervals. The first one, typically, it's self-weight. We will apply the self-weight in 10 steps. The self-weight and load that is defined in the boundary conditions is already like 100%, so we don't need to multiply it more. We will just divide it into 10 steps. So the self-weight, we need to add also the load cases that are applied during this interval. So we need the weight, where is the loading, and we need to add the supports, which are divided in this case into 2 load cases, which are supports and fixed contact. So the next interval will be just loading. That will load the structure. We will divide the loading into 20 steps. And this is like load force. That is where is our loading for this interval. Then we need to add support and fixed contact as well, that the structure is held together. Then in the third interval, we apply the corrosion load case. And here comes that assignment of the total condition. We will apply it in 20 steps, and that leads us, mistaken, yeah, and that leads us that the interval multiplier should be 20, that the step multiplier here is the 1. But ATENA actually knows which are total ones, so it should be done automatically. But sometimes it's good to be careful that those total conditions always have like each step multiplier 1. And then we go to the last interval, which is overloading, where we are going to test the load-bearing capacity of the structure. And divided into like 50 steps, and this one there is about like millimeter, so we will try to get more millimeters deflection. So the multiplier is 52, and so we need to add both cases. Support, displacement is what we are applying as a load for overload, because I'm keeping everywhere Newton-Raphson solution parameters. So for overloading or searching for the peak, it needs to be the load with displacement, not with the forces. Yeah, and maybe it's visible a little bit in here that when I was talking before about the time mapping function, it starts like after 30 steps, there is 0 time, and in 50 steps, which is like at the end of corrosion interval, it will be 100 years. So this is like what is connected to the time mapping function. Okay, so
Michaela, you forgot to add the load cases to the corrosion case.
Oh, sorry. Thank you very much. That is really bad. Okay, support, corrosion, and yeah, fixed contact. Thank you. So yeah, I'll just rather double check it, like first interval, second, okay, so one thing that you can also, like from time to time, if you are working more with ATENA and you are aware of INT file, checking it from time to time, you can also check some parameters, like if the functions are written correctly as it should. Like this is the time mapping function from 30 steps to 50 steps, like from 0 time to 100 years. And these values should be always already transformed into the values that are this default unit system that you select as a user. You can change it, of course, but the values that are written in here, everything should be converted to those units. When I maybe scroll down a little bit to the part where we have 730. So here's like carbonation, and there will be also the chloride. boundary conditions. So here you have all the parameters that are necessary to define the load. And this is exactly how those parameters you will find written also in ATENA manual. That is for ATENA input file. So this is something that you can double check if you are not certain what that parameter means. You can check how it's written in the INP file and in ATENA manual of INP file. You can double check it what sort of parameter it should be. Okay, so we can run it in the ATENA Studio, and that will take a little bit time, so I will just hide it with this to let it run a little bit faster without needing to like draw the results or something. And I will jump into the presentation again, and we can finish the presentation with the alkali-silica reaction, how it is considered in ATENA, because we have the model that have like combines three effects. It's ASR kinetic, then the moisture influence of the environment, and also alkali-silica content, which is related like how big strain there can develop. So this ASR kinetics is expressed with reaction extent T, and it basically depends on how like this ASR extent shows like how quickly it develops depending on the temperature the temperature of like conditions where it happens, the ASR, because temperature of the conditions how the ASR is developing is very crucial for it. So here is like general graphic expression how the ASR kinetics can develop, and it's described with latency and characteristic time. And this latency and characteristic time you usually have for one curve at one temperature, which would be at the moment reference temperature for that latency and characteristic time. Maybe it's good to point out that this characteristic time, it's basically distance between inflection points, like inflection point at the top and also at the bottom, where is this like biggest expansion, or like the fastest development of the reaction. And this characteristic time is like half of the distance between those two inflection points. And if those inflection points, like they have a little bit like different changes of curvature on both sides, you can just take the like mean value out of those. They can be different on each side, and there is like latency time from this point to the beginning. And so usually you have this latency and characteristic time for one measurement of reference temperatures, and then ATENA can like recalculate it for another temperature where the ASR is taking the reaction. These like this is again like interface in ATENA preprocessor, how you are inputting the parameters for the boundary condition of ASR. And here are parameters for this like development. There's a button in here that you see and UL that is like relating the parameters, those TC, TL, or tau C, tau L for different temperatures. You can keep them like this. There is a little bit range that you can change them in case of you have like measurements for different temperatures, then you can calculate, of course, as well. then you have that characteristic and latent time at certain temperature that is measured. So that was the kinetics, how quickly the reaction is developing. Then there is also like volumetric expansion of ASR swelling that has some limit too. And it depends on the reactive aggregates content and proportion of soluble silica, the alkali that are required for the reaction, and how much they were consumed and so on. And also the strain, that is like the strain that is tested on the free expansion sample where it's free expansion of, caused by ASR. Yeah, so then you have like this information also and written in parameters in preprocessing. During the preprocessing, there are also some like for numerical purposes, some other parameters like step increment. That is something that is relatable a little bit to those characteristic and latency times. And ATENA is reducing it. If it is like too high, ATENA will reduce it automatically on the background. The iterations, that is something that it's not necessary to increase them usually. And beta shape factor, this is something that is taken from literature that is connected to compression that can reduce the ASR like propagation if like the example the sample that has this ASR happening there is compressed or constrained. It can be limited, and there is this beta shape factor. You can find also a little bit more information in theory manual. This like ASR mode is something that you can, as a user, choose if the ASR will affect the strain development, or if it affects like the material properties reduction, mechanical properties of concrete, or if you want to consider everything, that then you have like all of this considered. This is the material properties reduction. That is something that you can have some tests, so maybe you can adjust it a little bit with these beta parameters, so you know what is like reference mechanical properties, and you can reduce them. And there's also like these two parameters. This one -10 is like 10 megapascal. That is also reported in literature. That is compression that is high enough to completely stop ASR. And this other limit, like just 0.3 megapascals in compression, that is something that you can limit also, like when this effect of limiting of ASR due to compression is completely omitted. So if it is like somewhere in between, it has some sort of weighing factor in the strains that are caused by ASR. And if it is above this, it's completely stopped. If it is below this, then the principal stresses don't have any effect on the ASR strains. Yeah, and finally, there is like ASR environmental, like effect of environment, which is the relative humidity, and that is usually considered relative humidity of the concrete itself. And here you can see like what is considered as a development, that until the relative humidity is below 75%, that there is no ASR happening, and when it crosses the 75%, it will grow. And you can actually adjust those limits as well in ATENA if you want to like reduce the lower limit. Yeah, finally, this is like one of the examples that were simulated in ATENA, that you have some experimental values, and you can also get some ASR expansion thanks to our software. And this is like mostly what we have here for ASR. And I would like to check if we managed. Oh, it's a little bit slower than I thought. Yeah, but I actually have the calculation already here finished. So I hope that I didn't make a mistake and I did the same calculation, that I didn't change some parameters. I will not mislead you with different results, but it should be the same result. It was mostly what I wanted to show you as how to work with results from durability analysis, how to find the reinforcement corrosion and so on. So what is interesting, like when you have the structure and you can check the crack width, which I actually here limited for sort of like visible cracks. So you can see where are mainly the cracks, because as the model is as it is like designed, it should always like cause more harm where it is cracked, where it like chlorides or carbonation can penetrate easily. So where we can see the cracks, it should also be visible on the results for like carbonation and chlorides. And I actually have here like chlorides. This is the concentration, how what is the resulting concentration of chlorides. It's maybe good to point out that this concentration, because for chlorides, the concentration is developing from the surface towards like inside of the structure. It's not the same everywhere. It's like highest on the surface and it decreases as it is penetrating. So the concentration in this case is showing on the surface, but its result in the concrete cover depth that you entered and in the boundary conditions. So it shows the concentration of chlorides on the level of the concrete cover. And you can also see the induction time for the structure, that basically in those areas where it is cracked very much, that induction time basically is like it starts immediately. There is no need to wait for like bigger concentration of the pollution. And similarly, you can check it for carbonation. There is like induction time as well. It's nicely visible. There was a difference between like chlorides and carbonation, that for chlorides I used different concrete cover depth. That's why there is much difference, like especially on the top here. But for the carbonation, I used the concrete cover everywhere the same. So here you can see how nicely it's visible where the structure is cracked, that the induction time is shorter. And then you can also check the carbonation depth, how deeply the carbonation already reached. It's not like with chlorides, because with chlorides you have like different concentration of chlorides, how it is like propagating through the structure. In carbonation, it's like either it's there or it's not. So that's like that where it already is happening. The carbonation, it can already trigger the corrosion of steel. Yeah. Okay, and the last part is actually like in here I switched it to 1D elements only, which will show you reinforcement. And also in here sometimes it's good to show the outline model if you have like relation to other pieces. And in the results here, you need to switch to from nodes to element nodes to find the corrosion. Then when you scroll down, there is like reinforcement corrosion. And you can divide it for like chlorides, carbonation, or you can see total corrosion. So it's actually visible. Again, like the effect of cracks, because you can see it mainly like in these parts where are some stirrups that are more corroded, or also on the flange here from the bottom. It's a little bit visible that there are pieces that where the structure is cracked, that it's propagating faster, that there's corrosion happening faster. For carbonation, it's very much nice visible, exactly like the area where it's corroding. And you can also see like the total result, how it is corroded. It's mostly like, have a look inside, it's mostly stirrups that have problem because they are of course closest to the surface. Yeah, and here is like LD diagram where it's also visible that since like corrosion started, there is no extra load, there is no reaction that is growing, but the deflection is still growing because it's propagating the corrosion and cracking. And this is like the last thing that I wanted to mention as well. When you compare this like durability analysis, when you consider corrosion load case, where actually corrosion happened, that it can really like significantly, like more than 40%, nearly 50% drop of the load bearing capacity for the same structure without considering the effect of the environment. So yeah, it can be important. Well, the timing is actually not bad. So I just like first wanted to thank you, of course, for the attention, and I wanted to also point out that we have email address where we are trying to be helpful with my colleagues. If you have any like questions and you don't have them now and you might have them later, that you can always reach to us and yeah, ask if you need any help. So anybody has some questions? Yeah,
I had a question.
Okay.
But it's a different topic.
Oh, okay. Let's see.
I tried to model the pull-out concrete cube, and somehow, like also in the ATENA preprocessor, and it's not working somehow. So I don't know, maybe it's the boundary conditions.
Yeah, it's hard to say without like looking at the model, but you can definitely send us on the email here the model, and we can have a look at it. It's always like a little bit easier to see the model and going through it.
Yeah,
so
yeah,
no problem.
yeah. But in general, it should be possible to model it, because I saw it on the video you did in Git, and it's also possible to do it in the preprocessor.
Yeah, it's
Okay.
it should be the same. Like, of course, it's not the same like environment, but
Yeah.
there are no limits for this.
Okay, yeah. And also, for example, the 3D concrete printing modeling can also be done in the preprocessor.
Not yet, unfortunately. I mean,
Okay.
it's like on the background if you put it directly in IMP file, but it's not yet in that interface like environment for that is more user friendly, of course. But it should be in the next version, like 2026, I think,
Okay.
if I'm not mistaken. Maybe Jan can correct me.
Okay. Thank you.
You're welcome.
Yes, there was a question about the 3D printing. Yes, indeed, this is not available now in the 2025. So if you need to model a 3D printing, you have to do it in Git. Or alternatively, as Michaela pointed out, it can be done by directly modifying the input file, which is of course possible. And it should be in the next version. We call it 2026, and we expect to release a beta version of this new version sometimes this fall. So maybe in November should be available as a beta version. Oh, there's one more question by Asdam that his microphone was not working. Yes, indeed, the recording should be available, or the recording will be available on a YouTube channel. In addition, we will send a message to all registered participants when the YouTube video is available. Okay, I think with that, we thanks again, everybody, for joining our webinar. And well, we are all looking forward to seeing you either at some conference or exhibition, or also at some future webinars. There is one more question by Muhammad in the chat. Can we generate non-uniform meshes in radial direction around crack notch in beam? I'm asking this for ATENA preprocessor. Well, you can, because you can always assign a mesh refinement to along particular surface or line. So that means if you have some locations where you want to have a mesh refinement, then you, of course, it should be related to some edge in your model or to some entity in your model. So then you can assign finer mesh to this line or surface or whatever is there, and then there will be a gradual transition of the mesh from that point outside.
Yeah, I would maybe just add from my experience that there is possible to assign the size of mesh, or like count in which pieces that part should be divided. And actually that dividing into pieces is usually, I have better experience with it than the size of mesh for like refining specific parts.
Yes, this is a good point. Okay, so with that, thanks again for your attention, and looking forward to see you some other occasion. Goodbye.
Okay, thank you very much. Bye-bye.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.